In this video, we're going to look at the details of the mathematics of the fast inverse square root algorithm. Now, in order to understand it completely, we're going to have to understand a little bit about floating point numbers. Now, I have generated several courses on floating point numbers, and that's how to generate a 32-bit floating point unit. Now, obviously, part of the course on Design a CPU 4 is to take that 32-bit floating point unit and then generate a 16-bit version of it. Now, before we go through and look at that over the next few videos, we're going to have a quick look at an intuitive comprehension of what we mean by floating point numbers. And it's something that tends to be maybe described in terms of the mathematics, and in the mathematics you can kind of get a little bit lost, and it maybe doesn't become quite clear and apparent how simple and how elegant it really is. So before I go in and crack on and look at a little bit of the mathematics of our 16-bit floating point numbers, let's have a quick 5-minute chat here about what it all means. So the first thing is that within a computer, we want to represent all of the real numbers. Now we've got a problem with that because we go from, say, minus infinity to plus infinity, and if we think about it as a continuous number line, then the number 0 is right at the centre. Now we're going to have an infinite number of numbers. So obviously we don't have an infinite capacity within our computer, so we can't represent every single number. It's just not possible. So we can only ever represent a subset of the real number line. Now if we've got a 16-bit floating point unit, then we can represent a certain number of a certain amount of this real number line, so a subset of it. If we've got a 32-bit, we can represent more numbers, and of course 64 and 128 and 256. And as you go up, you're quickly able to represent a much larger subset of numbers. So we've only got 16 bits at the moment. So what's the idea of a 16-bit floating point number? Well, if we take it quite simply, and I'll talk my way through it here just live, okay? I'll try and get a little description to you, and then we will look at the details. So if we take the 16 bits, we're going to think about the very first bit. Now, whenever I talk about the first bit, I'm not talking about a most significant bit or a least significant bit, okay? Because we can't really talk in terms of most significant bit and least significant bit, because we're not talking about a binary number, okay? But what we could say is the bit that is furthest to the left, if you like to say it like that. So the very first bit on the left, as you look at the number, is going to be the sign bit. So I like to split this into 3. So we're going to have a sign, something called an exponent, and something called a mantissa, or the actual correct name for it is a significant, but I tend to use the word mantissa, and it's just my personal preference, okay? So the very first bit is the sign bit, and it's very simple. You know, if the sign bit is a 0, then the number is positive. If the sign bit is 1, the number is negative. And you can say, well, why is that? Well, that's just what we've chosen whenever they generated this number system, which is the called IEEE 754 floating bit single precision numbers. So this is us, if you think about it, we're really like a third of the way there. You know, or we could even say we're even more than that. We're halfway there. We're able to represent 1/2 of the number line, and we're able to represent the other half of the number line. So we know how to make numbers positive, and we know how to make them negative. We simply put a 0 at the front, and it's a positive number. And we put a 1 in the first bit, and it's a negative number. Really simple. Now, the next 5 bits on our 16 bits floating point number are what are called the exponent. Now, the reason it's called an exponent is because it's raised to a power. So if you think about it, we want to represent as many numbers as we can on the number line. So what we can do is we can break the number line down into ranges. And that's an important word, okay? We're breaking it down into a range. So if you like, if we forget about the negative numbers for the moment, because we know how to generate those, and just look at the positive numbers. If we take the first range, and let's say the first range is actually between the number 1 and 2. Okay, so it's a little block between 1 and 2. And then let's say the next range is between 2 and 4. And then the next range is between 4 and 8, and 8, 16, 16, 32, 32, 64. Okay, so you get the gist of it. The exponent is going to tell you what range your number is in. So if you like, it's going to tell you which block of the real number line that your number exists in. Now, that's us really, if you like, 2/3 of the way there. Now, the last part of it is, within each of these ranges, we want to get the actual number. So within the range, we're interested in another important term, which is called the precision. Okay, so the precision is the granulation, or if you like, how accurate the number that you can get within each of the ranges. And this is given by the mantissa. So in the 16-bit number system, 16-bit floating point numbers, we're going to have 10 bits for the mantissa. And the way it works is these represent the fractional values. So if you like, the first bit of the mantissa is the number 1 upon 2. The next bit of the mantissa is number 1 upon 4. And then 1 upon 8, 1 upon 16, 1 upon 32, 1 upon 64. And you can see as you work your way along the mantissa, you're going to get smaller and smaller fractional values. So whenever we take the sign, and we take the exponent, and we take the mantissa, and we multiply them all together, the sign is obvious, we know what that gives us. The exponent gives us the block at which your number exists, and that is the range. And the mantissa then tells you whereabouts within that block your number exists. So this is the precision within the block. Okay, so it's kind of like someone giving you directions to your address for your hometown. Okay, so you can say that you're living in a country and there's 100 towns in the country. Okay, so the if you like, the exponent tells you which town you're in, and then each of your towns might have a zip code or a postcode. Well, the zip code or postcode is like the mantissa. Okay, so that's a very kind of broad ranging way to look at it, but that's in essence what is happening with our floating point numbers. So I've tried my best to try and give a quick kind of intuitive understanding of our 16-bit floating point numbers. Let's go now and we'll spend 5 minutes just looking at an example of a 16-bit floating point number, and it should become a bit more obvious, and there's a little bit more detail in the mathematical description here as well. So let's crack on and we'll have a look at that just now. So we have a 16-bit number here. We know that the first bit to the left is the sign, and I've got down below here S for sign. We know the next 5 bits are going to be for the exponent, and then the next 10 bits are going to be for the mantissa. So whenever you look at this here, what you should see is sign, range, and then precision. So the sign is obvious. The exponent range tells you whereabouts in the number line you are. Are you between 1 and 2, 2 and 4, 4 and 8, 8 and 16, so on and so forth. And then this number here for the significance tells you whereabouts within that range your number is. So this is the precision. Now, a little bit of the mathematics and a little bit more detail here. If we were wanting to write this out as a conversion to a decimal number, then the conversion is going to be given by this equation here. Minus 1 to the power of s times 2 to the power of e minus b. So e is the exponent, which tells us the range, and we've got a value b, which is the bias. So this is one extra little bit of complication, which I'll talk about in just a minute. And then the other part here is the mantissa. So the mantissa has got the value of m, which is the fractional part, but we actually do something really neat here, and it'll become obvious in a minute why we do it. We add on this extra term of 1. So this 1 is what we call a hidden bit. We don't see this 1 up in here because we don't need it to be here. We always convert using this process, and we always add 1 on to the mantissa. We know we're always going to have to do that, so we don't need to actually represent it within the 16-bit floating point number. What would happen if we did put it in to the 16-bit floating point number? Then it would mean that we'd lose one value of precision from the mantissa. So the mantissa in effect would just be like the 10 bits, but one of the bits would be a hidden bit, and then we would have 9 bits. But we don't need that first bit here for the value of 1, it's understood. So if we leave that out, we can get the full 10 bits of precision. It's quite smart actually. So this is how we're going to represent it. Now we can see here that if we look at this floating point number here, we know that that's a value of 0. So we know that that is a positive number. So why is it written like this? Well, this is just a little bit of mathematics. So if we look at the 3 blocks here, the sign, the exponent and the mantissa, we're going to have a value 0, which is positive, or 1, which is negative. So this little thing here, minus 1 to the s, well, s is just the sign bit. So in this case here, we've got a sign bit of 0. So if we say minus 1 to the power of 0, so anything raised to the power of 0 is just a value of plus 1. Okay, so that means that we're going to have plus 1 for the first part here. So that's just telling us we're going to have a positive number. Now, if it had been a value of 1 in this first bit, then we would have minus 1 to the power of 1. Anything raised to the power of 1 is just itself. In this case, itself is the value of minus 1. So if it was a 1 in the very first bit, then we would have minus 1 times what's left over. So therefore we would have a negative number. So this is just a little mathematical trick in order to generate the positive and the negative values. It's quite smart. So this has looked at the sign bit. So the exponent bit is the other 5 bits here. So if I was to look at these 5 bits here, we could say that these 5 bits, if we were to look at them in terms of binary and say that's the least significant bit and that's the most significant bit, then we would have the number 1, 2, 4, 8. So that would be the number 16. Okay, so we would have the number 16 decimal. So that would mean that the exponent here would be a value of 16. So this is the e here. So that would be, we would have 2 to the power of 16. Now, it's not just as simple as having 2 to the power of 16. We've got this other thing here called the bias, and this is the thing that tends to throw people some of the time. Now, if we wanted to represent the range, say from 1 to 2, 2 to 4, 4 to 8, then what we really have is we're going to have 2 to the power of the value of 0. So 2 to the power of value of 0 is a value of 1. So the next one is going to be 2 to the power of 1, which is a value of 2. And then we would have 2 to the power of 2, which is a value of 4, and then 3, which is a value of 8, and 16, and 32, and 64. Okay, so it means that using this 2 raised to the power of this exponent is going to give us the ranges 1 to 2, 2 to 4, 4 to 8, 8 to 16, and so on and so forth. But it's not going to give us the very, very first range, which is all the fractional values between 0 and 1. Okay, so in order to get all the fractional values from 0 to 1, we're going to have to do something, which is we're going to have to introduce this thing called a bias. So how does this bias work? Well, in order to represent the numbers between 0 and 1, these are fractional values. So for example, if I had the number 1 upon 2, so this is just the number a half. Well, the number a half, that's the same as writing 2 to the power of minus 1. So the exponent here is negative. So in order to represent the fractional values, we need to have a set of negative exponents, not only positive exponents. So for example, again, if we had something like the number 1 upon 4, well, 1 upon 4 is just the same as 1 upon 2 squared, which can be written as 2 to the power of minus 2. So you can see here, in order to get the numbers between 0 and 1 and have a good precision within that range 0 to 1, we're going to have the negative exponents. So for example, minus 1, minus 2, minus 3, 4, 5, 6, and so on and so forth. So we're going to have to not just represent positive exponents, but negative exponents. And we do that by using the bias. Now, in this instance here, for our 15-bit or 16-bit floating point number, what we do is we split the exponent range almost in half. Okay, so half of the exponent range is going to represent numbers greater than 1, and the other half of the exponent range is going to represent numbers between 0 and 1. So you might be looking at that and thinking, well, that's no very good, is it? Because if we could represent the entire exponent range without the bias, then we could represent numbers all the way up to between, say, 2 to the power of 30 and 2 to the power of 31. Okay, we can get that from these 5 bits. That would mean we could represent really large numbers. And you might think, well, why do we cut down that range so much so that we can represent just a set of numbers between 0 and 1? Well, first of all, we need to represent the numbers between 0 and 1, and we need to have a reasonable amount of precision. So to get that precision, we are going to have to split the exponent range in some manner. Okay, and it's actually more important that we get the precision down between 0 and 1 as opposed to getting the larger range, that is from, say, 2 to the power of 30 to 2 to the power of 31. It all works out a lot better. So it means that we maintain still a large range, but we still get a nice precision down at the lower values. And these are design choices whenever the IEEE 754 system was first developed. So what we do is we introduce this bias. Now in the bias here, the bias value is a number of 15. Okay, so in the 16-bit floating point number system, this bias is 15. It's very similar to when we looked at in different courses generating positive and negative numbers, and we introduced a a bias in order to represent the negative numbers and the positive numbers in our binary system. But anyway, if we were to look at this here, the bias within this is already there. Okay, the bias has been already added. Okay, so whenever you look at a floating 16-bit floating point number, it already includes the bias. So in order to get back to what is the actual value for the exponent, you always have to take the bias off. Okay, so in this case here, we've got the exponent here, which is 16. But to get the actual exponent, we take off the bias. So when we take off the bias, we get 16 minus 15, which is a value of 1. Okay, so it means that this thing, e minus b, just gives us the value of 1. So we know that we're going to have the plus 1 here, and then we're going to have 2 to the power of 1. So this one tells us it's positive, and this one tells us it's within the range 2 to the power of 1. Okay, so 2 to the power of 1 is 2, so it's going to be between 2 and a value just before 4. So we're within the range 2 to 4, but whereabouts within that range are we? That's what we get from the mantissa. So if we have a look at the mantissa here, we've got all these values here for the mantissa, and I've taken a note of them here. And we've mentioned before that we add a value of 1 on. This is a hidden bit. So we take this number here and we add 1 on. So when we add 1 on, we just have the 1 at the front. So we're going to have 1 in effect. Well, this would be a decimal point, and we would have the rest of the mantissa. Okay, now we know that this here represents the first bit of the mantissa is 1 upon 2, and then it goes 1 upon 4, and then it goes 1 upon 8. Okay, so 1 upon 8 is in fact the value of 0.125. Okay, so that's actually a full stop there. Okay, it's 0.125. So we're going to have 0.125. We're going to add on the hidden bit. So that gives us number 1.125. And then we multiply that by 2 to the power of 1, which is just 2. And we multiply this by the value of 1, which is the positive number. And this gives us the number 2.25. Okay, but it's really quite straightforward. It's just telling us that we have the sign, we have the exponent, which tells us the range, and then we have the mantissa, which tells us whereabouts within the range the number exists. So one last thing before I finish this video, because it's gone on for quite a while, is that in the 16-bit number system, we're going to have 10 values here for the mantissa. So if you look at 2 to the power of 10, 2 to the power of 10 is 1024. So we can think about the range box between 2 and 4 being split into 1024 little sub boxes. And we could look at the range box between, say, 4 and 8 also being split into 1024 boxes. Okay, so that gives us the precision within each box. Okay, and you might look at that and think, well, that means that when we work our way further along, for example, we went from 64 to 128, we're still only going to have 1024 boxes. So as we work our way up our number line, our precision is actually going to drop down, and that is a fundamental factor of the floating point number system. So that's enough for this video. We can't go on and talk about the fast inverse square root algorithm, because the fast inverse square root algorithm derivation, in order to understand it, you have to actually understand a little bit about floating point numbers. But we've got enough here to allow us in the next video to then go through a derivation of where this algorithm actually comes from. So it's a long video, but thank you for listening. Stick with it, and maybe try generating a few of these floating point numbers yourself. Also, I have a tool which will do it automatically, which I will show you over the next few videos. So thank you for listening. I'll get you on the next video. Goodbye.